Welcome to Section 4, Lesson 9. Across the previous 8 lessons, we built every algebraic and geometric tool for working with single linear equations and inequalities on the coordinate plane. Today, we apply all of those tools to the most common practical use of linear algebra, linear modeling of real-world quantities. A linear model is just a slope-intercept equation equals max plus b, in which the variables and parameters have specific real-world meanings. The slope m is a constant rate of change, the intercept b is an initial value, and the variable x is typically time, units, or some other input quantity. Once a linear model is established, you can predict the output value y at any input x within the valid range of the model. Today we lock in the linear modeling workflow and walk through 2 clean real-world examples. First idea on the board, a linear model is an equation of the form y equals mx plus b in which x, m, and b all have specific real-world units and meanings. The variable x is the independent input, often time or quantity. The variable y is the dependent output, often cost or position or amount. The slope m is the rate at which y changes per unit change in x, with units like dollars per hour or gallons per minute. The intercept b is the value of y when x equals 0, often interpreted as a starting value or initial condition. Second idea, to build a linear model from a real-world description, identify the input variable, the output variable, the constant rate, and the initial value. The rate becomes the slope m, and the initial value becomes the intercept b in the slope-intercept template. Plugging in gives the model directly. The hardest part of linear modeling is identifying the 4 pieces correctly from the English description. Once they are identified, the algebra is straightforward. Once a linear model is built, you can use it to predict the output value at any input value by direct evaluation, exactly as we covered in Section 2. You can also use it to solve for the input that produces a specific output by inverse operation solving, exactly as in Section 3. The 2 operations together turn the model into a powerful prediction tool. Always note the valid range of the model. Linear behavior often holds only within a specific input range, and extrapolating outside that range produces predictions that may not match reality. Today we walk through one increasing rate model and one decreasing rate model, illustrating both positive and negative slopes in real-world contexts. A linear model is an equation y equals mx plus b in which the variables and parameters have specific real-world units and meanings. The variable x is the independent input, often time or quantity. The variable y is the dependent output. The slope m is the constant rate of change, and the intercept b is the initial value of the output when the input is 0. Here is the modeling workflow. Step 1. Identify the input variable and its units. Step 2. Identify the output variable and its units. Step 3. Identify the constant rate of change with units that match output per input. Step 4. Identify the initial value, the output, when the input is 0. Each step is a small interpretation of the English problem statement, and getting all 4 right produces the model directly. Step 5 in the workflow. Plug the rate as the slope m and the initial value as the intercept b into the slope-intercept template y equals mx plus b. The result is the linear model with specific real-world meaning, ready to use for prediction or for solving inverse problems. Always write the units alongside each parameter so the model stays interpretable as it is used in later calculations. Step 6. Use the model to predict y at any input x by direct evaluation. Substitute x and compute y. The prediction is the model's estimate of the output at that input, valid within the model's valid range of inputs. Real-world quantities sometimes deviate from linear behavior outside the valid range, so always check that the input is within range before trusting the prediction. Step 7. Use the model to solve for x given a target y by inverse operation solving from Section 3. Subtract b from both sides and divide by m to get x equals the quantity y minus b over m. The reverse direction is just as common as the forward direction in real applications, and the literal equation skill from Section 3 Lesson 4 handles it cleanly. The forward and reverse directions together give complete predictive power over any quantity that follows a linear pattern. Here is the first worked example. A cell phone plan charges a $30 monthly base fee plus 10 cents per minute of usage. Build a linear model for the total monthly bill as a function of minutes used, then predict the bill for 200 minutes and find the usage that produces a bill of $50. Step 1. Identify the variables and parameters. The input variable is x equals minutes used in the month. The output variable is y equals total bill in dollars. The rate is 10 cents per minute, which equals $0.10 per minute, so the slope is m equals 0.10. The initial value is the bill when 0 minutes are used, which is just the base fee, so the intercept is b equals 30. Step 2. Build the model. Y equals 0.10x plus 30. The model says total bill in dollars equals 0.10 times minutes used plus $30 base fee. The units check the slope multiplied by minutes gives dollars, and the intercept is dollars, both summing to dollars on the y side as required. Step 3. Predict the bill for 200 minutes of usage. Substitute x equals 200 into the model equals 0.10 times 200 plus 30 equals 20 plus 30 equals 50. So 200 minutes of usage produces a $50 monthly bill. Step 4. Solve the reverse direction. Find the usage that produces a $50 bill. Set y equal to 50 in the model and solve for x. 50 equals 0.10x plus 30. Subtract 30 from both sides. 20 equals 0.10x. Divide both sides by 0.10x equals 200. The forward and reverse calculations agree, with 200 minutes producing a $50 bill in both directions. Step 5. Check the valid range. Real cell phone plans typically have an upper limit on minutes before different pricing kicks in, like a maximum allowed usage or a transition to overage rates after some threshold. The linear model is valid only within the range where the constant 10-cent rate applies. Extrapolating to 10,000 minutes would give a $1,030 prediction that might not match reality if the plan has overage rates that differ from 10 cents per minute. So the linear model is y equals 0.10x plus 30, predicting a $50 bill for 200 minutes. The big lesson from this example is the 4-piece identification step that converts the English description to a slope-intercept equation. Input minutes, output dollars, rate 10 cents per minute, initial $30 fee. Once identified, the algebra is mechanical and the model is ready to use both directions for prediction and inverse problems. Cell phone plans, taxi fares, electricity bills with base charges, and many other rate plus fixed pricing structures all follow this same pattern. Here is the second worked example. A water tank holds 1,000 gallons and is being drained at a constant rate of 25 gallons per hour. Build a linear model for the volume of water remaining as a function of time, then predict the volume after 8 hours and find the time at which the tank is empty. Step 1. Identify the variables and parameters. The input variable is t equals hours elapsed since draining started. The output variable is v equals volume of water remaining in gallons. The rate is negative 25 gallons per hour, with the negative sign because the volume is decreasing, not increasing. The initial value is the starting volume 1,000 gallons. Step 2. Build the model. V equals negative 25t plus 1,000. The negative slope captures the draining behavior. Every hour that passes reduces the volume by 25 gallons, starting from 1,000 gallons at time 0. The slope sign is the only conceptually new feature compared to the cell phone example, and the negative sign is the visual signal that the modeled quantity is decreasing. Step 3. Predict the volume after 8 hours. Substitute t equals 8 into the model. V equals negative 25 times 8 plus 1000 equals negative 200 plus 1000 equals 800. So after 8 hours of draining, the tank still holds 800 gallons. Step 4. Find the time at which the tank is empty. Set V equal to 0 and solve for t. 0 equals negative 25t plus 1000. Subtract 1000 from both sides. Negative 1000 equals negative 25t. Divide both sides by negative 25t equals 40. So the tank empties after 40 hours of draining at the constant rate. Step 5. Verify by substituting back into the model. V equals negative 25 times 40 plus 1000 equals negative 1000 plus 1000 equals 0. Match. The model produces V equals 0 exactly at t equals 40 hours, consistent with the inverse calculation. Step 6. Check the valid range. The model is valid for t between 0 and 40 hours, the period during which the tank is draining and contains a non-negative volume. After t equals 40, the tank is empty, and the model would predict negative volumes which are not physically meaningful. Always note that linear models often break down at boundary conditions like an empty tank or a closed account. The model is valid only within the range where the constant rate assumption holds. So the linear model is V equals negative 25 t plus 1000, predicting 800 gallons remaining at hour 8 and 0 gallons at hour 40. The big lesson from this example is the negative slope case for a decreasing quantity. Water tanks, fuel reserves, account balances during withdrawals, and many other depleting quantities all follow this pattern. The model handles the negative slope with no special procedure beyond writing the negative sign explicitly. The valid range note is also important. Real depleting quantities reach 0 and stop, while the linear model would extrapolate to negative values, so always check the range before trusting any prediction. 3 mistakes that catch every algebra student during their first weeks of linear modeling. Each one is fixable with a small explicit habit applied on every problem. First mistake: using the wrong sign on the slope when modeling a decreasing quantity. A student looking at a draining water tank, a depreciating asset, or a depleting account writes the slope as a positive number when the correct slope is negative. The fix is to ask explicitly whether the modeled quantity is increasing or decreasing as the input grows, and write the slope sign accordingly: positive for increasing, negative for decreasing. Saying the direction out loud while writing the slope prevents the wrong sign error. Second mistake: swapping the roles of slope and intercept by treating the initial value as the rate or vice versa. A student looking at a cell phone plan with a $30 base fee and 10 cents per minute writes the model as y equals 30x plus 0.10, putting the base fee in the slope position and the rate in the intercept position. The fix is to read the units carefully. The slope has units of output per input, and the intercept has units of just output. Base fee is dollars, not dollars per minute, so it must be the intercept. Per minute rate is dollars per minute, so it must be the slope. Third mistake: extrapolating the linear model past its valid range and trusting the prediction. A student uses a tank draining model to predict volume at 100 hours when the tank empties at hour 40, getting a meaningless negative volume. Or uses a stock price linear model from a 1-month period to predict prices a decade out, getting wildly off predictions because the linear pattern breaks down over longer horizons. The fix is to always state the valid range of the model when building it, and to check that any prediction sits within that range before trusting the result. Extrapolation is the most dangerous use of any linear model and requires explicit care. Linear modeling is one of the most used techniques in all of applied mathematics, science, engineering, and business because so many real-world quantities follow approximately linear patterns, at least within limited ranges. 4 broad sectors below. In physics, the position of an object moving at constant velocity is a linear function of time, with the velocity as the slope and the initial position as the intercept. The kinematic equation position equals velocity times time plus initial position is exactly the slope-intercept linear model from today. Every introductory physics textbook starts with this simplest form of motion before generalizing to varying velocity and accelerated motion in later chapters. In finance, a simple interest savings account grows linearly with time when the interest is computed on the original principal only, with the slope being the principal times the interest rate and the intercept being the principal itself. Real bank accounts usually compound interest, which is not strictly linear, but simple interest models are still used widely for short-term loans, certain bonds, and many introductory finance scenarios. The skills you build today are the foundation for all of personal and corporate finance modeling. In biology and pharmacology, the response of an organism to a drug or chemical is often modeled linearly within a specific therapeutic range, with response intensity proportional to dose. Outside the therapeutic range, the response saturates or becomes toxic, so the linear model has a clearly defined valid range. Researchers and clinicians use linear dose-response models continuously when analyzing experimental data and designing treatment protocols. In business operations, cost and revenue functions are commonly modeled linearly. Total cost equals fixed cost plus per unit variable cost times quantity is the standard linear cost model. Total revenue equals per unit price times quantity is the standard linear revenue model with zero intercept. The intersection of the two linear models is the break-even point, foundational concept for pricing, capacity planning, and business strategy. Manufacturing, software, and service businesses all rely on these linear models continuously. 3 things to take with you from this lesson today. Linear modeling is the practical payoff of all the Section 4 work and is one of the most used analytical techniques across every applied science, engineering, and business field in the modern technical world. First, a linear model is a slope-intercept equation y equals mx plus b in which the variables and parameters have specific real-world units and meanings. The variable x is the independent input, often time or quantity. The variable y is the dependent output, often cost or position or amount. Identify the 4 pieces input, output, rate, and initial value carefully from the English description, and the model writes itself. Second, the slope m is the constant rate of change of the output per unit change in input, with units like dollars per hour or gallons per minute. The intercept b is the initial value of the output when the input is 0. Read the units carefully when building the model. Rate has units of output per input, initial value has units of just output. Wrong sign and swapped rows errors disappear when the units are tracked deliberately. Third, always state the valid range of any linear model when building it, and check that any prediction sits within that range before trusting the result. Real-world quantities often deviate from linear behavior outside specific input ranges, and extrapolation is the most dangerous use of any model. Linear modeling is a powerful tool but requires the discipline of acknowledging where the model holds and where it does not. Coming up next, the lesson called Section 4 Marathon, where every concept from Section 4 is applied back-to-back on a mixed sequence of plotting, distance, slope, line equation, parallel, perpendicular, half-plane, and modeling problems. The marathon is the natural completion of Section 4 and the practice format that builds the speed and pattern recognition needed for tests, contests, and the function-based work of Section 5.